Our second speaker for today is Stefan Bloemheuvel. Stefan is a PhD candidate at the Hieronymus Academy of Data Science in Tilburg, where he started working after obtaining his master's degree from Tilburg University in the domain of data science. His master's thesis, in fact, has been making, since his master's thesis, in fact, he has been making use of complex networks to model multidimensional data, such as relational or temporal data collected from sensor networks. These models can be useful, for example, when monitoring strain and vibration of a bridge, but also when participants of a large event are being tracked to detect when and where information hubs are being formed and how information is exchanged. This can also be an informal event, as Stefan could attest to, because his very first project in this area concerned student parties. Stefan, we're very much looking forward to your talk today.
Okay, thank you very much. And also thank you indeed for organizing this TAISIG Talk. I'm really enthusiastically to share my work with you all. So there we go. So indeed, my name is Stefan Bloemheuvel, PhD candidate at Tilburg University and also located at Hieronymus Academy for Data Science in Den Bosch. I'm going to talk today about time series analysis with help of graph neural networks. So a small overview of the talk. So first I'll explain what Euclidean data and non-Euclidean data mean, and also give an introduction about the data structure called a graph. Then I'll give a small introduction to earthquakes and seismic data, because that is the domain that I'm working on, and then tell you about the latest work that I performed, which is called time series analysis with graph neural networks. So as you're all familiar with, deep learning and all the efforts in deep learning have shown great success in mining patterns and several data-related tasks. And most of these successes are visible in data that contains a sort of grid-like structure, perfect grid structure, and also a system of coordinates to work on. Well, what does that mean? Actually, as we're all familiar with sound or images, this follows a sort of structure. So on the left you see a time series, which is, for example, some sound wave, and this is ordered in a chronological manner, and every moment in time is one step ahead and one step behind the other point in time. And if you look at an image is a sort of 2D grid where all the pixels are nicely organized. So this is the notion of like Euclideanness. But what if we have data that does not really follow this pattern? Well, non-Euclidean data can be, for example, a road network or a molecule data set. So a road network consists of all these specific roads that are connected to each other. And you can imagine that the roads in Amsterdam or in Tilburg are much more densely connected than roads in other parts of the Netherlands. And if you would look at a molecule, which is the figure on the right, these are connected by all these different atoms. They can have different connections between them, and that completely changes the molecule. So this, of course, does not really follow some sort of structure. So how do you learn on this kind of data? So what researchers have done is represent this kind of information with a graph. And this is a sort of data structure. And it's also visualized here in this figure. And it consists of nodes, which are the dots that you see, and also the edges. And that are the gray lines between the dots. So on the left, you see that the nodes are numbered. So node 5 and node 6 are connected to each other. And this again, this can be a road network, which I've shown, but it could also be a specific type of molecule. But there's this issue, because we're going to talk about learning on this kind of data. The issue is that this data is so different from these images or sound data that we need some different techniques to learn on it. And here you see a small example of how a typical convolutional neural network would do such a task on an image. I'll explain it briefly for those of you that are not familiar. You see a toy robot image on the left and a small gray box. And What the image is trying to explain is that it will slide across this image and generate features from it to eventually funnel the data into another representation so we can learn from it. And the output would, for example, be, hey, this is a toy or this is a robot. But there are some challenges in doing this technique on a graph because, if we look at these molecules again, they all have different kind of atoms and they have different kind of connections, and also these connections can have different strengths. So there's this lack of consistency in the data. And if you would look at data sets of images, you will find that most of them have all the same dimensionality in the sense of that all the pictures have a 500 by 500 pixel width. So here this would not hold. And another issue is that these data sets of graphs often have node and edge level features or kind of information that you might want to include as well in your analysis. So imagine that this is again this figure, but now it's a network of cities. City 1 could be Den Bosch and city 2 could be Tilburg. If you want to calculate the estimated time of arrival, if you want to drive there, you would know the distance between the cities. It could also be interesting to know that there's a traffic jam ahead, and it's of 5 kilometers of length. So you want to incorporate that information. But if this was a social network, you can see it on the right side of the image a bit. I've drawn a little person there. If you want to learn from a social network kind of data set, you would want to know how many friends he has, how long he's on this network. So for example, his account age is 8 years old and his age is 22. So how do you include this information as well? So this general question that has been struck with researchers for the last couple of years is how can we translate this convolution procedure, that's this sliding a window over this image, for example, over to graphs, because that does not work. Well, it's actually pretty intuitive and elegant, and it helps by thinking of the graph in a different manner. And we therefore represent the graph in a JC matrix, which represents the nodes in the network. And here we see the JC matrix that is also visible of this figure on the right. So it consists of 4 nodes, and how you read these matrices is there's a 1 if there's a connection between 2 nodes, and a 0 if there's not. So if I highlight the 4th node, which is the last row, and there you can see there's no connection with node 1. Okay, that's clear. There are two 1s after each other. These represent the connections with node 2 and 3, and there's no connection with itself. So there's a 0 as well. Okay, so now we have this representation of the graph. What can we do then? Well, it turns out that if you multiply that adjacent matrix with a feature matrix, and these features are just pieces of information about a node. So that could be the number of friends you have in a social network, or your account age. If you do a multiplication with the adjacent matrix and this feature matrix, you actually get a new representation that is just the sum of the neighboring features. So, okay, what can we do with that information? Well, I'll first explain how this again works. So I've highlighted node 4, and it is connected with node 2 and 3. They have these features 1, 1, 2, 2, and these get summed together. So this new representation of this node will be 1 plus 1 is 2, and 2 plus 2 is 4. And again, if you do this for the node 2 in the graph, there's a bit more connections. There's a connection with all other nodes in the graph. Now it will sum together to 3 and 6. So thus, a convolution on the graph can be thought of as a sort of message passing. You give each other information about yourself, and then you can learn from that. So then, okay, this is like the building block of this model. Then there's this really interesting paper of Thomas Kieft and Hans Welling that made this all a lot better with their graph convolutional networks, and it's a really popular paper in this field. They've included self loops into the JC matrix because it's also important to include your own features. And also some normalization tricks are applied because if a node has a lot of features, their sum will be really high, of course. You don't want that. That leads to some instabilities in training. This is not the only model that is apparent. There are many others. So diffusion convolution, edge convolution, gravitation networks, you can name it. They're all implemented in the spectral package, all based on Keras and TensorFlow, if you're interested. So what kind of tasks can you do with these graph neural network models? You can do node classification. So let's see that we have this network of movie enthusiastic people, and you know that the green ones, they like thriller movies, and the orange colored nodes, they like rom-coms. Given that two new people join this network and start making friends, could we maybe predict what would be their favorite genre? Or you can do something with the entire graph itself. You could classify the entire label of the graph. Given again this molecule example, maybe we know from our training data that some of them are toxic and some of them are not. Could we maybe predict from the structure in this network and the atoms that are in there if this is also a toxic molecule? And lastly, another type of analysis that can be performed is that you can predict a link in the network given attributes of other nodes in the graph and what kind of example connections there already are. So perhaps these two people, node 4 and 3, should be brought together. And this is exactly what Twitter or LinkedIn do to give you recommendations for friends. So this was a small introduction into graph neural network research. Now I'll talk a bit more about what kind of research I'm doing with these techniques. And this is applied on earthquake data. And earthquakes are actually a really great candidate for doing graph neural network research because there's an enormous amount of data already gathered at these seismological stations for over like 50 or 60 years. And these sensors are geographically grounded. So we know the latitude and longitude information. The data is recorded by sensors and is really crucial for seismologists. So they use this data all the time to say something about earthquakes that occur. And typical use cases are determining the epicenter of an earthquake and also estimating the magnitude of one. And it can be used for early warning. And that is exactly what I did. So to give an earthquake early warning, you have to look at this earthquake data. And earthquakes actually give a lot of hints about themselves. So they send out different waves when it occurs. So in this picture on the left, you see that a fault is occurring, there's an earthquake happening, and it shoots these waves into the ground. There are some lighter P waves, but also more slower later on S waves and surface waves, which are way more damaging. So if we can take hints from this P wave, we could perhaps predict how intense these S waves will get. So that's exactly what they do by placing all these sensors in areas where there's a high chance of an earthquake occurring. And then we can notify people. So how does this look like in a more schematic view? So on the left, we see a red star, and this is its earthquake epicenter, and it starts to show its waves to the nearby stations. These waves are visualized in the middle of the figure, so you see some of them see it fairly soon, but most of them see the rumbling way later. And the task of early warning is that you look at the initial seconds of this dataset. So we have 25 seconds of data, but we only look at the first 10 seconds to say something about what happens in the later on periods of the earthquake. And what we're trying to do is do a regression task because we want to say something about how intense this earthquake is measured at all the stations in our network. So we perform a regression task to predict 5 numbers which characterize the earthquake. And why is this important? Well, a few things. So there's of course public warnings that we can give to people to find shelter, but also first order mobilization. So we can already open fire station doors for rapid deployment of fire trucks. We can notify hospitals. So in the healthcare, we can stop medical procedures for people that are undergoing surgery. And in mass transit systems, we can prevent trains from colliding or derailing by the shaking of an earthquake. And also we can clear bridges of vehicles. So that brings us to my paper, which I recently submitted. Could we make use of the spatial information of these sensors to perform a regression analysis and improve predictions? And that is exactly what we did. So we made a new paper, graph neural networks for multivariate time series regression with application to seismic data. And what is really cool is that I worked together with 2 actual seismologists from Italy. So it's a really cross-domain collaboration, also international collaboration, which I always find really interesting. So by modeling the stations in a seismic network as nodes in a graph, we can apply graph neural networks on the signal data. And you can see them right here. We use 2 datasets, 2 that are completely different from each other. So on the left side, you see network 1, where it's a really densely connected region, and also the earthquakes shown as orange dots are really densely connected. On the right, you see another network, also in Italy, it covers a larger land area, and also the earthquakes are more scattered around. So it's a bit of a tougher use case. We made a model, which is really unique actually, that first uses standard convolutional neural networks to generate features from this earthquake data. And then the main premise of our paper is that we show that you can actually use the output of these CNN layers as input in a graph neural network layer by reshaping the size of this convolutional network. And then eventually you can use it for certain tasks. We did a regression task, but you could also apply it for classification, for example. So concerning the results, we compared our model against the CNN baseline that was created by the seismological experts from Italy, and also other traditional machine learning algorithms. So K-nearest neighbor, XGBoost, random forest. And we saw great results. So we had an average mean squared error reduction of 17.9% on both datasets compared to the best performing baseline, which was the CNN. And this is actually really remarkable because keep in mind that the only information that we've added was the notion of this graph. So this is only one time calculated before you do the analysis at all. So with a little bit of effort, you get a really great reduction in error. And even more interesting, of course, we're trying to give early warnings. The earlier warning, the better. And we tried reducing this input window length to see how far we can go. And it turned out that we can halve the input window length of our graph neural network model while still achieving similar performance to the baseline CNN. And I hope you can see it on the figure on the right. You can see that we have such a head start that even with 5 seconds of data, 50% of the data, we can similarly score compared to the CNN. So this is really crucial since we're trying to give off early warnings. So in conclusion, we've shown that graph neural networks excel at learning from features that have a spatial grounding. And from our paper, we have seen that graph neural networks can learn from these sequential time series features generated by CNN. So that is really crucial. For future work, we want to investigate the scalability of our model to sensor networks that are of even larger size. Now we investigated 39 stations in both of these networks. We are interested to see what happens when we increase this number to 200 or even 500 nodes. And also we want to try transfer learning techniques. So perhaps we can train on one network and then transfer some of this knowledge onto another network so we don't have to retrain all the time. That would be of really good value for the seismological community, they've told us. So thank you for watching, and if there are any questions, let me know.
Thank you, Stefan, for a very interesting talk and for a nice introduction into the domain, which we appreciated. I have a question about potential implementation of your research results.
Mm-hmm.
So we know that these techniques can be quite time-consuming in the phase of training, and that they can be quite demanding also when they're implemented. Now, this concerns an early warning system. How does that work in practice?
Well, eventually, how it works in practice is that you continuously monitor the data that's generated by these sensor networks. And you could supply this data in batches to the neural network to make a prediction. And luckily, we also saw that the model size of the graph neural network is also even smaller than the original convolutional neural network. So you can actually run it on fairly simple computers to make these predictions. So that's how normally this works. You give it in batches.
Yeah, thank you. The second question that I would like to ask is about transfer learning. So can you imagine that the results that you obtain for this particular data set could be actually used, the pre-trained model could be used also in other domains that might have similar properties?
Yes, I think so as well. What you could, for example, do is test it on weather data. So weather data also has kind of different characteristics. It has a somewhat short-term pattern. So in a day, the temperature changes really a lot. But the course of a season, there's this longer pattern. So I hope that the graph neural network can actually grasp that as well. But other kind of domains that are actually are using these techniques is predicting traffic networks, on predicting the estimated time of arrival. So I know that Google implements this in Google Maps. So given the speed data of all these people that are driving around on roads, would you make predictions better? You could also use techniques here. So a lot of companies and also researchers are finding out new domains where these techniques can be used. So let's hope we see some other creative techniques as well.
Thank you very much.